Welcome. In this lesson we will understand decorators from the ground up. We will begin with why they exist, then build the concept step by step using first-class functions, manual wrapping, the syntax, and best practices. After that we will cover advanced topics like parameterized decorators, stacking, class decorators, async support, and production-grade tools from FuncTools. Each code cell includes a narration block followed by a natural description of what you will see when you run it so the video stays clear even without your console visible. Why decorators give Python an edge? They reduce repetition by centralizing cross-cutting behavior like logging and timing. They keep business logic clean by separating concerns. They allow retrofitting behavior without editing the original source, which is valuable for libraries and restricted code. They enable declarative intent so a reader sees the policy attached to a function in one glance. They compose like building blocks so you can layer caching plus retries plus tracing in a predictable order. This approach improves readability, testability, and long-term maintenance. A decorator is a callable that takes a function or class and returns a new callable. It attaches reusable behavior like logging or timing without changing the original source code of the target. The idea is driven by the don't repeat yourself principle and separation of concerns. In Python this is natural because functions are first class so we can pass them and return them from other functions. We define a simple function hello. Then we define useFunc that accepts a function and calls it. Finally we define makeAdder which returns a new function that adds x. This demonstrates that functions are values which enables decorators. Expect 3 prints. First a prologue about to call the function value then hello then done. After that you will see add 5 of 12 gives 17 which confirms closure behavior. Now we will manually decorate a function without the syntax. We will write a decorator function that takes a function, creates a wrapper that adds extra behavior and returns that wrapper. Then we will assign the decorated function by hand. Decorator func accepts a function and returns wrapper. Wrapper prints pre and post messages and calls the original. We then manually decorate greet by assigning decorated greet is equal to decorator func greet. Prints 3 lines in order, before call then hello user then after call, proving the wrapper added behavior. The syntax is only a shorthand that applies the decorator at definition time. Python translates the line above the function into an assignment where the original name is replaced by the returned wrapper. This keeps intent next to the function so readers instantly see that logging or policy applies while avoiding boilerplate assignment lines. Using the syntax, process payment is replaced with the returned wrapper during definition. Calling process payment therefore runs the wrapper which prints before and after the body. Expect running process payment then processing amount 500 then finished process payment. When we wrap a function we usually lose its name and docstring because the wrapper replaces it. This affects debugging help and introspection. The standard fix is FuncTools wraps which copies metadata from the original into the wrapper. Tools like help tracebacks and test reports show the original function name which improves developer experience. First we show the problem where the decorated function reports the wrapper name. Then we fix it by adding the wraps decorator to the wrapper definition so metadata is preserved. You will see bad name wrapper bad doc none followed by good name target 2 and its original docstring. Decorators must handle arbitrary arguments because different targets have different parameters. The common pattern is to accept star args and ** quargs in the wrapper and pass them through to the original. This keeps the decorator generic and reusable. One decorator can work for many signatures, so you avoid writing variants. We define trace that prints the function name and the arguments it received. It accepts args and quargs, then calls the original with the same values. Expect paired lines around each call with start and end plus the output value for both power and join names. Sometimes the decorator itself needs configuration such as a level label or threshold. In such cases, write a decorator factory. The outer function captures parameters and returns the real decorator. Configuration is now declared at the function site, so behavior can vary per function without new code. We create log with level that returns a decorator which prints the chosen level. This is the standard pattern for parameterized decorators. 2 lines with info markers appear around the function call, then total 60 is printed. You can stack multiple decorators. The application order is bottom to top. The closest decorator to the function runs first at call time because it is applied last at definition time. This enables composable behavior like timing plus logging plus caching. Small focused decorators can be combined to build richer behavior. We define 2 decorators, timer and unknowns. Stacking them shows the order of execution. Expect starting slow task, then a delay, then a line with took seconds near one point to then ending slow task and finally the word done. Decorators are not limited to functions. They can decorate classes too. A class decorator receives the class, mutates or returns a replacement, and gives you a hook to register or enforce policies. Here we add a readable string method to any class automatically. You can inject common behavior across many classes without repetitive boilerplate or inheritance hierarchies. Add str adds a str method to the class. We apply it to person to get a friendly print. A single line appears showing the class name and the instance dictionary, for example person was, name, Samir, age, 35. A decorator can also be implemented as a class by defining call. This is useful when you need state that persists across calls, such as counters, catches, or dependency handles. The class receives the function at init time and is then called like a function. State is encapsulated next to the behavior while still using decorator syntax. We implement a counting decorator as a class. It stores the wrapped function and increments a counter on each call. Each call prints the running count before returning the Fibonacci value, so you will see calls so far lines followed by the numbers for fib 10 and fib 12. The FunTools module ships with powerful production-ready decorators. LiRiCache adds memoization. Cached property turns a method into a lazily computed attribute. Single dispatch enables function overloading by type. Wraps we already used to preserve metadata. These tools add performance and clarity with one-line changes that are easy to apply and revert. We cache a slow add using LiRiCache. The first call waits about a second due to sleep and prints the sum. The second call with the same arguments returns almost immediately with the same result, demonstrating caching. Decorators are used extensively in frameworks to declare behavior. In a web-style example, you decorate functions to register routes or apply authentication. The example below mimics the idea without requiring a web server. It shows how a decorator can register a function in a table. Registration and discovery become implicit, so adding a feature is a single definition line. Route registers functions in a global table. When we later call dispatch with a path. the correct function is invoked. This mirrors how frameworks register handlers. You will first see the list of known paths, then simulated results for two known routes and the string not found for an unknown path. Async code can also be decorated. The wrapper itself must be async and must await the target. This pattern is common in async frameworks for logging timing and retries. You apply the same cross-cutting ideas in asynchronous programs while keeping signatures clean. Async logger prints start and complete around an async function. We then run it with async queue. Expect two lines starting and completed around a short pause produced by the sleep call. Let us collect best practices and common pitfalls. Always use wraps. Keep wrappers thin and focused on one concern. Prefer args and quargs for flexibility. Be mindful with stacking, as too many layers can hide the core logic. For debug or profiling, you can expose the original through an attribute if needed. Also avoid capturing mutable default state in closures unless intentional. Following these rules keeps decorators helpful rather than hidden complexity. A tiny utility to expose the original function when needed. The decorator attaches original for introspection. One line prints the phrase original is demo. Original followed by a number, confirming that we can still call the undecorated function directly. You now have a complete mental model plus the reasons decorators are valuable in Python. Use them for logging timing, access control, caching, validation, retries, registration, and async tracing. A decorator is a callable that takes a callable and returns a callable, enabled by first-class functions and used to attach cross-cutting behavior cleanly. Thank you for watching and learning. If you found this notebook helpful, please like the video and subscribe to the channel Notebook Learnings for more Python and AI-based tutorials.